Okay, good morning. We can continue yesterday's discussion. And I would like to focus for today's class on the calculus part. And so we have the polar system, and we are going to use calculus method. Okay. And I think last time I'm showing you this, right? So this one is actually when you have 1 plus c, or if I mentioned that we have r equal a plus minus b. So we can also change this a and b with c. So c can be b over a. So we can have r 1 plus minus c sine theta, r 1 plus minus c cosine theta. This is another way to write the equations, but that should be the same. Okay, either with the left one or the right one. Okay. But if you see this one, so if we change the ratio, we're going to change something that has this loop, okay, small loop, and when equal 1 is perfectly cardioid. And this is going to be less than 1. Okay. And then if we get it closer to 0, it will be getting similar to circle. Okay, so it will be close to circle. And then if we getting less and less, it becomes negative. It means it's going to be a downside now. So because it's sine. Okay. It will be the same thing with the cosine. Cosine will start from the right, and then you change the c, you make it less and less and less. You will get later it will be on the left, okay, for the cosine. Okay, and it will always the same pattern. Okay, every we say the limason or the cardioid. Okay. Here. Okay. Okay, now let me just conclude what we have in the polar curves. We can have a normal circle like this one, or a circle with the multiplication of sine or cosine, which is sine and cosine over there. Okay. And spiral. We can also have a spiral. So a spiral depends on the constant. We are going to have something like that. Okay. And then this is limason. Okay. Now this is using a and b, which means that this r is a plus minus b. So whenever a is less than b, so for example, it's 1 is 3, here you will see the loop. Okay. You will see the loop. If a equal b, like 1, 1, then it's b cardioid. If a is greater b, maybe 2 and 3, this will be a dimpled limason. And if a is greater to b or equal to b, it will be a convex limason. So it's like a circle, but it's not symmetrical, okay, in the y-axis. Right? That's limason. And then for the four-leaf or the roses, the flower, there is some pattern that you need to realize. So the first one, we have done this, right? So r equal a cosine 2 theta. We have 4 leaf rows. So notice that we have 2. So 2 theta. So we have 2, but the total number of the leaf is 1, 2, 3, 4. 4. So if it's 2, it's 4. Now let's see when we have 3. If we have 3, it's 3. Okay. But if you have another 4, it will be 1, 2, 3, 4, 5, 6, 8. So it's getting double. It's getting double. If you have 5, it's staying the same 5. So if it is odd, If it's odd, the number is the same as the n. If it is even, it will be 2n. Okay. And then, the last one, we can have what we call the lemniscate. So lemniscate only has two forms. If we have sine 2 theta, it's like this, like a diagonal. And we have cosine 2 theta, we have like an infinite number, right? The symbols. So we write the formula r squared, a squared, and then sine 2 theta. So we have r squared and a squared. Okay, and then that's all the special curves in polar. Okay. Actually, some of the sections in the problem solving, they also mention that we can combine, for example, combining this one with the limason. So every here it has a loop and then another loop. Okay, you can imagine, right? Like imagine you have a cardioid like that, but it's going into 4 different shapes, right? We can also combine that, but I don't think that is necessary for our course now, so we can just focus on the special curve. Okay. Now I would like to move to the calculus part. Okay, so that's the introduction on polar. Okay, polar coordinates and the polar curves. Okay. So to begin with, let's start with So let's start. Let me write here. I forgot to write the title. So calculus in polar. Okay, I will make some summary at the first introduction here. Okay, so imagine that this is a piece from a circle. Okay, so imagine like a pizza. Okay, you cut and then you take one piece like this, right? So it has a radius r, and it has angle theta over there. So the area of this piece, we call this is the sector. Okay, this is the sector. We call the sector. The sector, it has area. If you forget how to find, we can find with the ratio in angle, right? So theta over 2 pi and then multiply with the pi r squared from the circle. So we get half r squared theta. Okay, and then this formula or this sector area we are going to use to get into the area of the curves, okay? our curves. Let me copy this first. Maybe move this a little bit to the here. Okay. So if we draw a random polar like this r equal function of theta, so this is our polar curves, and imagine that this is the polar axis, okay? And we can have an angle theta equal a and theta equal b. Okay? We have two angles. And then we would like to evaluate between this A and B some area R. Okay. Now what we can do is we are going to approach this area using this formulation. Okay. And now let me just get into the how to get the formula in more details. So let's say let f is a positive and then continuous function, and then the angle is between b minus a until 2 pi. So we are going to define the interval from a to b into small area. okay, as we see from here. Okay, so we define all and becoming a small area. So the small sector. Okay, and you could guess obviously from this area when we cut into small pieces, the more it will be more accurate if we can cut this like into small pieces, and we could approach with the sector. So imagine that you can have like a really small, and then we can approach this with our sector, and then we can plus those from this angle to this B. And I think you could see that that is the form of integrations, right? It's the form of integrations. So let's say in between this, let's say this is maybe this here. Let's say this area is our delta A, the small area that we already have cut in pieces. So it's called the delta A I. I means it's sampling. Okay. Let's say it's approximate by our half, and then this is R. R is function of theta. Let's write theta I for sampling, and added the asterisk. Usually added the asterisk. It means that we can do this for every small pieces, and then take the square, and then take the delta theta. Okay, this is none other than our sector. Our sector, right? And then the small pieces we can combine. Okay? So we can plus all the small pieces, plus. So we can approximate A using the sigma, right? The summation. So we add all the sector area, okay, within some interval, within small interval, and then we can plus all those small area, right? So we can write A approximate with the sigma from I equal 1, from the sample 1 until some n, let's say some n. We can make n as much as possible, large number, right? And then we can write half and then we can use our definition on integral, which are already mentioned in terms of the sum. So the area becomes a limit. So we can make the n as big as possible. So area is, and then we can say the endpoints from the first interval A to the end of the interval B. How? Function of theta d theta. Or in another way, we could simplify this, becomes A to B half r squared d theta. And that is the area on the polar curves. take this a little bit the middle. Okay, and then now some example. Okay. So I think if the polar curves are simple enough, you can easily see that you just need to plug in the curves into R, because the polar curve will be a function of theta, and then you plug in the interval A and B, which angle that we want to evaluate. Okay. But the problem is if the curves may be not easily to be observed, so we need to at least check either if we have intersections or maybe we have some more than one polar curves, okay, and that will be a problem to be solved usually in the exercise. Okay, now let's move here. Let me just give you an example here. Let's start with a obvious example. Curves. The rose curves are equal cosine 2 theta. So find the area enclosed by one loop. So we're right here. So find the area enclosed by one loop of rose curve R equal cosine 2 theta. Okay. And I given the picture. Sometimes the question doesn't include the picture, so you need to draw first to sketch the curve. Okay. And sometimes, if you remember how we get this curve, to avoid mistake, my suggestion, because at certain point, this cosine has a negative value, right? Like for example, we start from here and it goes here, right? So this part here is actually the curve made by this angle, right? So the best way to do this, okay, if we are maybe trying to find 2 loops or 3 loops or 4 loops, we just multiply this one loop with 2, 3, or 4. Okay, that's to avoid mistake. If we try to make out the angle, maybe we made mistake and we have mistaken the angle. For example, we want to take this. Which angle that is? If we're using the angle on the curve here, we say, oh, maybe this is from pi over 4 and then this one here, right? But that is wrong. This one should be here, right? Because it's going there, right? Because of the negative. The cosine has a negative. So to avoid mistake, you can make sure that the one that you are evaluate here are the angle that is on this curve here, right? Okay? I hope you get my point. Because, for example, if your radius is negative, your point is on the other side, right? On the other side. Basically, on the polar curve, on the paper, you will not see any negative, right? Because r is just a distance. But cosine and sine has a negative. So to make it that, then we are going to have an opposite direction, like I mentioned yesterday. Okay. So be careful on that, and just using the one that is confirmed and that is there. Okay. So for example, one loop here. Okay, if you want to multiply with 2, with 3, with 4, you get the whole area, right? Okay, because it's symmetrical. So the curve we can take, because it starts from negative pi over 4 and then to pi over 4, so we get the area. And then just plug in the formula. And a little bit calculation. Okay, now we have cos squared 2 theta. Okay, now how to solve this? Okay, remember, if you have just a normal integral, we have trigonometric sine or cosine that has squared. The best way to solve this, use double angle, okay, to remove the square. Okay. So taking the cosine to theta is cosine squared theta minus sine squared theta, or 2 cosine squared theta minus 1. Since it's a 2 theta, so we have cosine 4, right? And it's become cosine squared 2 theta minus 1. Okay. So we are going to have, now let me write here, is half this will be half cosine 4 theta, right? And then plus half, or maybe cosine 4 theta over 2, maybe better. And then integrate with respect to d theta. Okay. Now I think we can integrate easily. So cosine becomes sine. Okay. So half, this is sine 4 theta, and then over 8, right? And then plus half theta. And then evaluate from negative pi over 4 to pi over 4. And then, to avoid mistake again, I forgot to mention, we can also make this just half and then multiply by 2. It's also can be done because it's symmetry. Okay. So if you want, we can make it 0, 0, 0, okay? Or you could make it afterwards. I'll just replace this minus pi over 4 with 0 and then multiply by 2. So I will remove the half, right? So remove this, and then this becomes 0. And remove this. And then remove this. Okay. 0, 0. So sine pi is 0, so pi over 4 multiplied by half, it's pi over 8. And I think it's easier, right? So whenever you see any symmetry, you can just cut in half and start from the other one, and then multiply by 2. Okay? Or maybe to get, let me write down here to let you know that we have 2, and then we have half here. So the radius 2 is because of the symmetry. Okay. Okay. So key points to solve this integral, aside from using the polar, is using the double angle to remove the square on the trigonometric. Okay. For trigonometric sine or cosine, we need to remove that, and the best way is using the double angle. This method will, I think, you will see a lot. Okay, so I hope you get used to use the double angle. Okay? Because of course we have the polar, and the best way to describe polar is using the trigonometric. Right? Now I'll give you another example. I think I prepare here. Okay, I prepare this one. This one, I'm using this one a lot in some exams. If you take my course before, you see this, I think, in the exam. So find the area, okay, in the region that is shaded, which means the blue one. Okay, find the area. So find this area. Of course, you need to have a little bit work for the algebra. Okay. So how do we do this? How to solve this? So we have, if you remember what we call this, is the Leibniz scale. This is a Leibniz scale, and the one here is just a normal circle with the cosine. So it's on the right side. So what should we do first? Any idea? Because in this area between these two polar, if we cut this, okay, so perhaps we cut this to see that we can have two different area, right? Area that is described by this, and area that is described by the Leibniz scale. Okay. So I think the best way is to find this point. What is this point? So first is finding the intersections, so that we know at what intersection that these both curves, they share the area. Okay. So we have two intersections here and here. So find intersection. Okay. So how to find? We just make it both curves equal, right? So r square root of 2 cosine theta is equal to, or because it's the lemniscate is r squared, let me write here. So r square root of 2 cosine theta, and r squared, we make it squared, so 2 cosine squared theta. Okay, so if we let this 2, I will directly write 2 cosine squared theta equal square root of 3 sine 2 theta. Okay. And then we are sure that this one is what we call the first quadrant in the system, right? Which sine and cosine, it must be positive value, right? So we should be safe if we don't worry about the negative value, right? So we say that we can, if we make this sine 2 theta becomes 2 sine theta cosine theta, we can cancel this cosine, right? So take that. Or maybe not yet to cancel, to avoid mistake. Okay, so that was my mistake. Sorry about that. So I think it's safe if we just take 2 cosine squared theta and then minus 2 square root of 3 sine theta cosine theta, because I'm afraid they have to set different values. So let this equal 0, and then we can factor it now. So 2 cosine theta minus square root of 3 sine theta. I think this is the safest way to solve this. If I did the previous one, I'm trying to cancel, maybe I will lose some solutions. So we see that cosine theta equals 0. Oh, this is the one that we can lose. Okay. We can lose this one. So we get two factors which describe we have two intersections. Right? Okay, I think this will be the correct one. If I'm canceling, I will just get the only 1 point. So we have 2 points, right? So cos theta equals 0. So theta can be pi over 2, and then cos theta equals square root of 3 sine theta. So tangent theta equal 1 over square root of 3 or 1 over 3 square root of 3, right? So theta will be pi over 6. So the factors, we get pi over 2 and pi over 6. So if we take a look what we have here, okay. If we start from this, okay. If we are going to move through this point. Okay, let me just draw a line. Okay, draw a line here. There. Line here. Okay. So if we have this, so we need to decide which one is our area. So we know that this is we get from pi over 6. Okay? So we have the theta equal pi over 6. And then when theta equal pi over 2, it goes down here, right? So we know that this is pi over 6 to pi over 2. Okay? Now you see that if we move from pi over 6 to pi over 2 from the circle, this area is our area of the circle, right? So this one this is area of circle R from pi over 6 to pi over 2. Okay, right? And then we have the bottom one here, right? So the bottom one is from the area of the Leibniz scale, this one, okay? From 0 to pi over 6, okay? Okay, so we have two areas to be combined. Okay, first is area of circle, and second is area of the scale, okay, with different interval. Okay. So to combine these two, we can just write area equal integrations from 0 to pi over 6, and let's say we start from the Leibniz scale. And remember, we write half r squared d theta, right? And luckily, our Leibniz scale is already r squared, so we can just use this. Sometimes, if you are not paying attention to the questions, you will make it squared, and you will lose some points. Because it's already r squared, so you can just use this. Okay. So write down half square root of 3 sine 2 theta d theta, okay, and then plus pi over 6 to pi over 2 is half, and now we have square root of 2 cosine theta and then square and then d theta. Let's make it on the left side first. Okay. And I think for the first one, we can integrate easily. Sine 2 theta become a negative, right? Negative cosine, right? So we can write square, or maybe the minus will come out like that. And then this will be cosine, cosine 2 theta over 2 from 0 to pi over 6. And then plus. So this turns out to cancel, right? This one will cancel. So we have cosine squared, which we can exchange to double angle. Half plus cos 2 theta over 2, right? And if we want to integrate this, then this will be half theta, right? So this will be half theta plus sine 2 theta over 4 from pi over 6 to pi over 2. Okay, now we calculate. Let me make this smaller. Resize the part. Okay, and then we can calculate so area. So we plug in pi over 6. So what we have now is half. So this one, let me write negative square 3 over 4 cosine pi over 3 is half, right? It's half. Let me write half. And then cosine 0 is 1. So minus 1, right? Okay. So half minus 1 minus half, so it will be positive. So positive square root of 3 over 8. And that's on the left one. On the right one, we need to check pi over 2 pi over 2, oh, pi over 4, sorry, pi over 4, and then plus 0 minus pi over 6, it's pi over 12, plus pi over, sine pi over 3 is square root of 3 over 2, so square root of 3 over 8, okay? Okay, I think we can just add those. So pi over 4 minus pi over 12 minus square root of 3 over 8. We can cancel this one and we can get pi over 4 minus pi over 12. It's 3 over 12. So it's 2 over 12 or pi over 6. Okay. Okay. The more you are getting used to how to compute the algebra expressions, I believe you will get faster to solve this. But even I think it doesn't matter as long as you get your complete formula here and it's correct. It's already halfway. You already get 50% on your answer sheet. If you have like a small mistake here, maybe you still get 80% to 90%. You still get almost complete, so it's still okay. Because everybody makes mistakes. Everybody makes mistakes. So I appreciate students who are, it's already correct, sometimes there are some professors, you really get this correct, and then maybe some small mistake here, and you get 0. Okay, but now I think if you don't get this, but you are getting correct here, you still get 80 to 90, 80 to 90%. Okay. Okay, I think we can have a small break. Okay, now we are having more examples. Now, the question is the same problem, finding the area, but the region is described by it lies inside the first curve, which means the left curve, and then outside the second curve, which means the right part. Okay. So let's try our best on maybe 24. Okay, 24. That is the first one. So try to work on 24. So first is perhaps try to sketch how it looks, and then try to find the area. Okay. And by the way, I just checked the calendar. I think I will adjust some sections because on the first week of October, I think from October 2nd to October 6th, I will not be in Taiwan. So I will prepare some recording video that you need to watch, and then some, maybe like a homework to do, okay? And then the university midterm exam schedule is from 23 October, right? 23 to 27. So if we can make it to the at least chapter 11 or chapter 12, then we can have the midterm maybe on 22nd October 22nd midterm. If not, maybe 1 week after. Okay, it means the November 1st week. Okay, our midterm exam. So I think some sections on chapter 12, I will give you just a recording video because I think the factors, especially the first introductions, I don't need to give you again, right? I mean, you guys already have more in physics, so I just review, just a quick review, and maybe emphasize which one that is going to be related to our calculus part. So after October, after the midterm, we can continue to chapter 13, 14, and 15. So we can, and then that will be the content for the final exam, 13, 14, 15. So for the midterm, it's 10, 11, and 12. But some part, like in chapter 10, we only finish up until this polar. So polar, calculus polar, okay. We have the conic sections and the conics in polar, that will be skipped. Okay. So until the 10.4. Okay. So try this one, okay, number 24. Okay. First is try to sketch first. Okay.
Very powerful.
It's really good. I don't know how to use it.
I think we can check YouTube. A lot of tutorials. So 1 minus sin Okay. Okay, so number 24. C 1 minus sine theta. Okay, if you remember what we did before, how to draw. Okay, this one here. So it should be cardioid, right? It should be cardioid. So I hope you don't need to try some angle and then make points too long, too much time to do. Okay, so remember, sine, the only positions it can have on the top, on the bottom. Positive is on the top, negative is on the bottom. This is negative. Right? So the cardioid, it will have large portion on the bottom. Okay, so probably it will be around this one. Oh, sorry. And perhaps that is, although it may be not really proportional, maybe make it like that. Okay. So let's say this is the R1, or maybe let me burn here, R, okay. And then what else? R equal 1. It will be on here. But how to confirm? You can check the intersections if they have the intersections. Check the intersection, make it equal 1. You will see that it will goes to 0, right? So at least 0 is when we have around this point here, right? So it will be 1, 0, right? So we could have that circle. So this is R equal 1. Okay. Now the question is lies inside the first curve. The first curve means the cardioid. So inside the first curve, but outside the second curve. So the second curve is this R equal 1. So outside, so it should be here, the bottom one, right? Okay. Okay, so this one is our goal. Find this area. Now after sketching, then we can try to find. Okay, let me write the intersection first so that you can have a clear picture. So 1 minus sine theta equal 1. So sine theta equals 0. So theta can be 0 or pi. So this will be 0. Here is 0. So this is 1, 0. This will be 1 pi. Okay. Okay, we have some sort of angle in between the curves, right? But now how to make sure that we are going to compute this area? Okay, if we take the cardioid from 0 to 2 pi, we include it all, right? All this cardioid. Now what we want is, we want this minus this part here, right? Okay, so maybe let me write here that 0 can be 2 pi, right? So we could make the computations from pi to 2 pi, okay, from here to that point. Okay. So what I want to make is, so let me write maybe here. So from pi to 2 pi, it means from this point here, from this pi, we are having this, right? This is 2 pi. We know this one using the cardio, right? Okay. And then if I take the circle over there, okay, can we know the circle? We can, right? The circle is r equal 1. And then if we are using the same interval from pi to 2 pi, we could make this the whole area of cardioid in this one, minus with the circle. Okay? Get it? So let's do that. So this one becomes a from pi to 2 pi half 1 minus sine theta squared minus 1. And then maybe make it bracket like that. Because 1 squared is 1, right? Okay. And then theta. Or maybe to make sure that you understand what I mean is maybe 1 by 1. So this one and then minus the same half d theta. And then we can rewrite this and make it all together half. This will be 1 minus 2 sine theta plus sine squared theta, and then minus half, or maybe not half, maybe minus 1, and then this will be minus 1, and then d theta. Okay, now again we have sine squared, which we can transform into double angle formula. So this will be half minus cosine 2 theta over 2, right? And then this part is getting cancelled. So we need to be careful. So half so we'll be having another half minus cosine 2 theta over 2 minus 2 sine theta. Okay, I think we can integrate. Let me move this, I haven't been told yet. So area is half theta So pi, wait. Sine squared minus 2 sine is okay. Cosine 2 theta. Oh, wait, this one. Cosine, sine. Okay, it's correct. Okay, let's continue. This half. So pi, right? And then plus 2. And then minus pi over 2, right? Okay, pi over 2. Is it correct? Put 2 pi, yeah, pi over 2, so pi over 4 plus 2, right? Oh, wait. 2 cosine this should be that will be correct. So plus 4, okay, I think it's correct now. Okay. Okay, a little bit long, but we can solve it. And I think mostly in the polar area, in polar, you need to be able to use the double angle a lot. So don't forget that. Okay, I've prepared this one, but I haven't mentioned how to get the line of the curve. So let's just go to the line of the curve. Okay. So that's the area. Okay. Okay, so let me write here the arc length. This is relations between xy and r theta. So as long as we can relate these two with the conversion of polar with from the Cartesian, for example, we know that this is our relations, right? And of course, this is for r equal function of theta. So we could start to write this x in terms of function of theta, cosine theta. Also the same thing with the y. So to find length of a polar curve, r equal function of theta, from A to B and the angle in between A and B. Then we are going to start to write, let's just write with r cosine theta, and then take dx d theta, would suggest you to get a, because r is function and cosine also a function, then we need to have a product rule, right? So it goes by dr d theta cos theta and minus r sine theta, so the product rule, right? And then the other one, y equal r sine theta, okay? And then dy d theta. Okay, and then remember the arc length we need to have in parametric. Remember we have dx dt, dy dt, we squared, and then we have a square root, right? We are going to do the same thing with our dx d theta and dy d theta. So we are going to square it, and it's getting a little bit long, but it's actually not really that complex. It's just a very long equations. So take this square, and then let me write here. So dx d theta squared plus dy d theta squared. Okay. So let's just square. It means we are going to expand the expression. So dr d theta squared cosine squared theta minus 2r dr d theta sine theta cos theta plus, now we move to dy, dr d theta squared sine squared, oh sorry, not yet finished. So we need to write r squared sine squared theta, and then move to the y, dr d theta squared sine squared theta plus 2r dr d theta sine theta cos theta. Oh, too long. Let's make it smaller. And then plus r squared cosine squared theta. Okay, it's long, right? But here's the deal. We have minus 2r dr d theta sine theta cos theta, and the other one the positive, right? So we can cancel this. Okay. And then in another forms, look at, we have sine squared, r squared, and then we have r squared cosine squared. We can combine this, right? We can also combine this with this. Okay, so let's do that. So dr d theta squared we can combine which this is just one, right? This is also one. Now in total, then we get dx d theta squared plus dy d theta squared is equal dr d theta squared plus r squared. Okay, we get these expressions. So the arc length now is from A to B of square root of r squared plus dr d theta squared d theta, and that's it. basically it's the same as what we have in the parametric, but we simplify it into the polar. So the idea, we kept this similar to what we have in parametric, right? In parametric we have dt, but it's actually the same thing. But what we have here is we simplify to r and the r dt. And we change with the polar expression. Okay. Okay, so area and then arc length, and we know after this we're going to see the tangent. Okay. So why we did the area first on polar? Because the area is the one that's significantly not really similar with the parametric. The arc length and the tangent, they are going to be very similar to what we have in parametric. So sometimes when you are given some equations, you can treat them in parametric, or if you can rewrite in polar, you can treat them in polar. Okay? When you are calculating the tangent especially, you can have two ways. Okay, so let's go to the tangent. Okay, I hope this one is okay. Yeah. So basically, if you forget what's the expression here, you can try to take x r cosine and y r sine, and then take the first derivative, means product rule, take squared, and then plus the result, and try to simplify it using the trigonometry identity, and you will get that it will result in this. Okay. And this is basically the same thing as this one, which in parametric we already have learned, right? So you just plug into the formula and then integrate, and that's your arc length. Okay? The same with parametric. Now if you look on the tangent, we are actually have the same approach. So when we have the tangent, so we start by taking x, and then also here the sine theta. So do the same thing. And then take another one. Okay, and then the very same thing, taking dy dx as our tangent. It means that this is going to be very similar with the parametric. Oh, wait, not dy, dx d theta. Okay, it means that we are going to take dr d theta cosine theta minus r sine theta. And that's it. Oh yeah. Why I'm writing here? Okay. Correct. Sorry about that. And then the problem also very similar. For example, finding the tangent, and then maybe the horizontal tangent, right? So horizontal tangent, we want to make dy dx is equal 0, then dy d theta needs to be 0, and dx d theta is not equal 0. Okay. So we can get through here for horizontal tangent, and we also can take the vertical tangent. This is when dy dx is approaching, let me just write infinity. And this is when dx d theta is 0, provided that dy d theta is not 0. So this one here. Okay. So if you are given a polar curves and you want to find the tangent, at least there are two ways to solve it. You can just go here and take the tangent like that, and just plug in and then take derivatives and so on and so forth. Or you change to x with r sine theta, r cosine theta, and then y r cosine theta, and then basically you can use the parametric if you can. But I think for the polar curves, only polar curves, I think the best way is just use this way. But sometimes if you want to write in a more detail, you can also use the parametric. Okay. Maybe giving an example on this one, okay, what kind of question that might comes up. Let me write here. And then after that, we can finish our lecture. So suppose r is 1 plus sine theta. First is find the slope of tangent line when theta equal pi over 3. And the second, find points where tangents are horizontal or vertical. So basically, you can take the x equal r cosine theta, y equal r sine theta. So if you perhaps you are not remember the exact formula, we can derive the formula together. So dy over dx, we can take dy over d theta, and then dx over d theta. Okay. So this will be dr d theta sine theta plus r cosine theta, and then this will be dr d theta cosine theta minus r sine theta. Okay. And then dr d theta, from the equation here we can get this is just cosine theta, right? So substitute all the components. Let's substitute. So dr d theta is cosine theta multiple sine theta, and plus r is 1 plus sine, and then cosine theta. Okay, just walk step by step. From small step, we could see later the bigger picture. And then this will be cosine theta. Let me just write cosine theta like that. Minus 1 plus sine theta, and then sine theta. Okay. Okay, and then let's simplify this. Let me write this from there. So let's factor out the cosine. So cosine here, let's factor out. So cosine theta, sine theta plus 1 plus sine theta. So 1 plus 2 sine theta, right? So 1 plus 2 sine theta, okay? And then the same thing here we can do now. I think we can just try to take this as a cos squared theta minus sine theta plus sine squared theta. So we get cos squared theta minus sine squared theta minus sine theta. So cos squared theta minus sine squared theta, I would like to change that into 1 minus 2 sine squared theta. So 1 minus 2 sine squared theta minus sine theta. So I will have the quadratic expression of sine. Okay. So this can be written as 1 minus 2 sine squared theta minus sine theta. Okay. So it's practically from this, okay, cos squared theta minus sine squared theta. That one, this one here, we can write as this, right? And if we have minus sine theta, this one, we can have I think a good expression for the quadratic expression. We can factor this, right? So we can factor it. And now we can have cos theta 1 plus 2 sine theta. This will be 1 plus sine and 1 minus sine. Oh, minus 2 sine, sorry. Minus 2 sine. Anyone still struggling to factor something, to factor the quadratic expression? Maybe we can write 1 minus sine theta like that minus 2 sine squared theta. Okay. And then we can start make a table like this. Make a table. And then I think we agree that for 1 we can have 1 and 1, no other numbers that can make it. And then for this one we can have sine theta and 2 sine theta, and this one can be negative or another one can be negative. We can check. Cross multiply is positive 2 sine theta, and then this will be negative sine theta. We plus them, it's positive. We need negative, right? So maybe this one, right? So that one negative. And then, okay, that is our factor. Right? We can check, it's negative 2 sine, and then this one is sine, so negative 2 sine plus sine is negative. So that's why it's our factor. I think for me personally, I'm getting used to using this method to find the factor. Okay, and then after that, oh, forget the brackets. We can plug in theta equal pi over 3. So as a little bit think calculations. So pi over 3 here. Then we can write half, right? So half 1 plus square root of 3, right? Square root of 3, because it's cancelled by 2, the half. And then this will be 1 plus and 1 minus square root of 3. What can we do now? I think we can simplify it. We can multiply 2 over 2. Okay. So we have 1 plus square root of 3 divided by 2 plus square root of 3, right? And then 1 minus square root of 3. And then what else? 2 minus 3, which is negative 1, right? Two minus 3 is negative 1, so this will be negative 1, negative square root of 3. Okay. That's the slope. I think you can try finding the horizontal tangent and the vertical tangent. Okay. And I will end the lecture about it here. We're going to have a few examples on your outline, and then we can move to new chapter, okay, chapter 11. So chapter 10 finished. So chapter 10 will focus on parametric and polar. Okay, just that. We skip the conic section, conics in polar, okay, no need to go through that part. And then we move to chapter 11 next week, okay? So I think I will just end up here.